One of the things I want to do this semester, as you go through different topics, is try to relate it back to COVID-19, hopefully to give you a better understanding of COVID-19 and how it applies to what you are learning. So if you can't see the detail in this picture, do not worry about it. I just took this from my Discover magazine that came out a few weeks ago. The first thing I want to mention is, as I go through these, what's happened with this virus has happened very, very quickly. And so what happens is scientists come up with ideas or try something and it may or may not work. So what was true in March or what we thought was true in March may not be true now. Or something that's true now from a scientific standpoint may not turn out to be true down the long run. A science is trying to move as quickly as it can on this virus and understanding it. So you have to kind of keep up to date. So as I go through these, I will say, as of this time, which is, August of 2020, this is what is thought. And in 6 months from now, they may find that that is not true. Now, the first few things I'm going through are going to be pretty factual. So first thing I want to describe for you, and you'll go through this later in the semester, but I wanted to introduce you to it now, is what is a virus? Okay, what is a virus? This is the SARS-CoV-2 virus. A virus is technically not a living thing because it cannot survive on its own. Now you learned about cells in this class as well as your other biology classes. Cells are living. You can take a single cell, it has all the structures it needs to survive. A virus does not. A virus is made of either DNA or RNA, and in the case of the COVID virus, it is made of RNA, and then it has this surrounding envelope to it, and then it has these little spikes on it. So it lacks things like mitochondria and Golgi apparatus and those kind of structures. So a virus, how does it survive? What the virus will do, the virus actually has to live or use another cell in order to reproduce. Now, before I get into that process, this is not a flu virus, okay? Coronavirus is not a flu virus. In the case of a flu, these little spikes, there are H spikes and N spikes. And so when you hear H1N1, that means it has H1 spikes and N1 spikes. There's H2N2. There's a whole bunch of combinations of these H's and these N's. So again, I just want to reiterate that this is not a flu virus, but just so you understand, flu viruses, they work the same way. They're just different in some of their structures. Okay, so how does a virus survive? If it can't reproduce on its own, what does it do? Well, what it does is, you learned about receptors on cells. Okay, there are receptors on cells. What these spikes can do is they can bind to certain receptors on certain cells of the body. They cannot bind to all receptors throughout all the cells of the body. They bind to very specific receptors. Right? Now, these receptors don't exist for viruses to bind to. They exist to do other jobs. But it just so happens that certain viruses can bind to certain receptors. For example, HIV, human immunodeficiency virus, its spikes, they can bind to receptors on immune system cells. So these spikes on the coronavirus, they bind to what are called ACE2 receptors. Okay, ACE2 receptors. These exist in different places throughout the body, but they primarily exist within the lungs. Now, I know you haven't had the respiratory system yet, so I'm going to give you a little intro here. So you have these structures here that brings air in to these cells that are called alveoli. Alveoli is where oxygen and CO2 move back and forth between the lungs and the blood of the body. They're very delicate cells, so there are alveoli here, and there are also a second type of cell that makes what's called surfactant. And what surfactant does, just real quick, you'll learn this later, it actually keeps these alveoli from collapsing. So on these alveoli and on these cells that make surfactant, there are these ACE2 receptors, especially deep within the lungs. Deep into the lung tissue, there are more of these ACE2 receptors. So what the COVID virus does, what any virus does to some respect, is it binds to a receptor, in this case the ACE2 receptor, that tricks the cell into taking that virus into itself. And then what the virus does is it takes its genetic information and it puts it into the cell's information, and the cell is being tricked into making copies of the virus. So the virus is using that cell's machinery that it lacks to make copies of itself. And then once that cell is kind of full of the virus, then the cell will kind of explode, not explode like with a big loud noise, but it'll kind of explode. The viruses will be put out into the bloodstream, and then those viruses will bind to other cells with the ACE2 receptors, and then again those cells will be tricked into making more and more copies of the virus, in this case the COVID virus. Okay. So what starts to happen is the virus starts destroying these cells. But it also starts attracting a response by the immune system. The immune system has ways of identifying when cells have been infected by a virus. And so you start to get this buildup sometimes of blood and fluid in the lungs as the immune system is responding to the virus and as these alveolar cells, alveoli in the other cells, the surfactant cells, are being destroyed. Okay, so a virus has to survive in another cell. So they don't have a very long lifespan on their own. So you may have heard, especially early on in the quarantine, how long can a virus survive on a surface? It can survive longer on cardboard than it can on steel or copper. Copper has actually been shown to actually destroy viruses pretty well. So they can't survive unless they're in other cells. Now they can survive for a time period, and then they will just kind of die off. They won't be able to infect anything. So that's the basics of how viruses work, and specifically the COVID virus, the COVID-2, binds to cells within the respiratory system. So this is why you hear about people developing pneumonia and then having trouble breathing and have to be put on ventilators because their system is not working because of this viral attack. Now, one thing you may have heard of, especially as we started school, is that young people, especially kids under 10, it's very uncommon. It does happen, but it's very uncommon for them to get infected and have severe side effects from this. Now, part of the reason for this is because younger people have less ACE2 receptors located throughout their body. So what this means is even if they're exposed to the virus, that the virus can't find a place to bind and it can't find a place to reproduce, so it's not going to survive. So what they found is that the older you get, the more ACE2 receptors you have, the more detrimental this virus can be to your body. Now, why is another reason that if you get infected, the older you are, the more likely you're going to have serious side effects? And that comes down to ACE2 receptors, but it also comes down to the immune system. As you get older, it depends on your health, but from 50 on, your immune system's not as good as it was when you're in your age group. So that's why you're seeing people in their 70s and 80s that are much more affected by this in a negative way. Now, it doesn't mean that young people aren't dying from it. They are, but just not at a high rate. It's amazing that even right before we went on quarantine, I showed a graph to one of my classes, and usually you're going to see young people, very young babies and young kids more affected by these because their immune system's not very strong either. And it showed that no children were getting this virus, and that was unusual. So when you have real little kids, little babies whose immune system is still forming, they usually get hit by some of this stuff, and they just didn't get hit by this virus. Now, again, I want to reiterate that it does not mean children cannot be affected. Your age group, they're saying, and that's right now, this is one of these science examples, this may change, that kids under the age of 10 have a very low, what's called a viral load. They don't have a lot of this virus when they're exposed to it. And so it's not as easy for them to pass it on to adults. And that's been one of the concerns with school, is that, yes, these young children may not be getting it, but are they going to pass it on to their teachers who may have a higher risk of being infected because of age or because of other health problems? So again, right now, it's thought that kids under 10 and younger, that they're not likely to pass it on to adults, but that may change. Middle school and high school, That we're not sure of. You guys are able to can carry a higher viral load than younger kids, and you're more likely to be asymptomatic, which means you may have the virus in you, you may expel the virus, you may not get sick, but you are probably more likely to pass it on to adults, people that are older, or to your own people in your own age group who maybe have health problems that make them more susceptible. So in your age group, things may be a little different. I mean, that's one of the reasons that you're not going to see me a ton this semester is because, I'm older, I'm 55, so I'm at higher risk. And then I have to be careful because if I go on a trip, then I don't want to bring it back to you. And if I go on a trip and I'm traveling with people, and one of the trips in September, I'm traveling with a person who's been a transplant patient and who's older, I don't want to take the chance of getting it and then passing it on to them. So that's why we have to be so careful. You have to think about your friends. There may be people in your age group that are more susceptible, but that's why we're seeing an age difference, they think. And again, that may change. Okay, so the other thing I want to talk about just briefly is the current treatments, and this may change over time also. Doctors are working on the fly here trying to save people. What's working, what's not working. One of the things that's working, and I actually learned this weekend, is that putting people on their stomach, laying on their stomach instead of their back. And the reason is your largest amount of your lung tissue is towards your back, and you'll see that when we learn about the respiratory system. And so if you're laying down, this fluid that's building up, if it settles in your lungs, in the bigger part of your lungs, you're losing more lung capacity, which means you're more likely to have severe problems. So they're actually trying to put people on their stomach. There's also some steroids out there, one called dexamethasone that's been shown to help. It's a steroid, so it decreases inflammation. So it's going to help with some of the side effects here of the virus. The problem with any steroid is a steroid, if given at too high of a dose, can actually decrease your ability of your immune system to fight an infection. So they have to give the people enough to try to help with the inflammation caused by the virus, but not give so much that they suppress the immune system and the virus has a better chance of surviving. So again, they're working on the fly here. They're trying to figure out what are the best doses. Science sometimes works slowly, and so we learn things constantly about what's going on in the medical field trying to help with this virus. Okay, so that kind of gives you an overview. It relates to cells and understanding the difference between a cell and a virus. Hopefully you understand now how the basics of how a virus can infect a cell by binding to a receptor, and then some of the health problems that can cause. And again, some of the things I told you again are going to change. Science is going to, medicine's going to find and do actual studies over time that's going to see what's actually going to work with this virus. Many believe that this virus is going to be around for a while. Let me go into one more thing. You've heard about trying to develop a vaccine against this virus. Most vaccines take several years to go out into the market because first we have to make sure they work, and then second we have to make sure that they're safe. People are working more quickly through this, trying to get a vaccine faster since this COVID is being passed so quickly from person to person. I can't tell you when that vaccine is going to come out, and they don't know how effective it's going to be. What a vaccine does, the basics of it is it 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 gives you, I'm trying to say this in a way to make it as simple as possible. It exposes you to a part of the virus or the DNA of the virus into your bloodstream and tries to get your body to develop an immune response against the virus without making you sick. So they can't just give you the virus because then you would get sick. They're going to give you a part of the virus that causes the immune system to develop a response so that if you are exposed to that virus, the whole thing, that your body will fight it off before it makes you sick. So that's the basics of a vaccine. Give you something that's going to cause your body to develop immunity against the virus. So if you are exposed to it, you will not get sick. It takes a while to do that. You've got to develop something that's safe. You have to develop something that's going to last a period of time, and that's their concern. is that we're showing that people that were infected with the virus early on, like in March, do not have an immunity to the virus. They've lost that immunity. So usually when you get exposed to a virus, like let's say the chickenpox virus, your immune system develops a response, and then for several years, if you're exposed to the chickenpox virus, you will not get sick. They're finding that people that had these antibodies that you hear about, they got the virus, they developed these antibodies, but that over only a few months, the amount of those antibodies has gone down significantly, so they're not immune to it. So there has been some speculation, and again, this is one of those things that may change, that people actually have been able to get it more than once, that are actually going to be exposed again and get sick again. So a vaccine doesn't help us if it only develops immunity for 3 or 4 months. We need something that ups your immune system so that when you're exposed to the virus for a long period of time, you will not get it. So that's been one of the issues is, can we find a vaccine that makes you immune to the virus for at least a year, so you'd be only getting the vaccine um, once a year instead of every 3 or 4 months. There's no way they can develop enough vaccines and get those out to everybody that quickly in that number. I am going to tell you that you are going to be doing an ethical thinking paper, and your ethical thinking paper is going to be about who's going to get the vaccine first. So once we do develop a vaccine, which hopefully we will, how are they going to give that vaccine? Who's going to get priority? How are we going to spread that vaccine throughout? We're going to focus on the United States where we have 330 million people. But how are we going to decide, or how's it going to be decided, who's going to get that vaccine first and who's going to have to wait for it? So it's going to be real world. This is the most real world ethical thinking topic that I've ever had in a class, is once we have the vaccine, how are we going to decide who's going to get that first? Okay, so that I know is a bunch of stuff. I just want you to get the basics. I want you to understand the basics of what COVID is and what a virus is. And again, as we go through the semester, I will talk about things that relate to COVID, that relate to topics that you're going over in class. Okay, see you soon. Or maybe not, because I might have to stay away more.